Hello everyone. Welcome to the first module of Essentials of Turbulence. The first module is called Fundamental Considerations of Turbulence. So here we are going to be looking at a few different things. I'll describe the sources, then from where the material is used. We start with the despair in turbulence. We'll try to answer a few questions like why study turbulence? Whenever we want to learn about a topic, we have to know why are we studying that in the first place? So why study turbulence? Another question I want to answer through this first module is what is turbulence? And as we are describing, as we are defining, trying to define turbulence, maybe let's start to look at some descriptions of turbulence, see whether we can understand turbulence through that, define turbulence through that. So that will lead us to, from the definition, it will lead us to looking at some attributes of turbulence, some basic characteristics of turbulence, something that is always there in a turbulent flow, something that distinguishes a turbulent flow from the other kind of flow, which is laminar flow. And finally, we look at a brief history of turbulence studies, what different mathematicians and physicists in the past, over the last 200 years, have done to understand turbulence. The different theories they proposed, the hypothesis they came up with, the results they found, the analysis, the conclusions, and summarize them through three eras of turbulence studies. What we will call the structural, statistical, and deterministic era. So we'll describe that, all of that in this module. So these are the sources that I have used for pictures and text extracts for the notes in this module. Starting with the despair in turbulence. So why do I call it a despair in turbulence? Maybe because it is such a complicated topic to understand. A lot of physicists have expressed a despair in different ways. I start with a quotation from Werner Heisenberg. Heisenberg, if you remember, he was a German theoretical physicist. He was one of the main pioneers of quantum mechanics. The Heisenberg principle is something that you've probably heard of. He was a principal scientist in the German nuclear program in World War II. And he was the author of the uncertainty principle. So his quotation, he said, when I meet God, I'm going to ask him two questions. Why relativity and why turbulence? I really believe he will have an answer for the first. So that was him expressing his despair in turbulence, meaning it's so hard to understand that maybe I should give up in that sense. Another quotation is from Horace Lamb, a possible derivative of the above quote, right? Horace Lamb, who was the author of the seminal hydrodynamics book, in 1932, addressing the British Association of the Advancement of Science, said, I am an old man, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other is turbulent motion of fluids. And about the former, I'm rather optimistic. So it's a very similar quote to what Heisenberg said, but in another way describing or expressing, I should say, the despair in turbulence. Another one by Safman. Safman was a mathematician at Caltech, and he was a PhD student of Bachelor who again wrote seminal books on fluid mechanics and turbulence. Safman said, we should not altogether neglect the possibility that there is no such thing as turbulence. That is to say, it is not meaningful to talk about the properties of a turbulent flow independently of the physical situation in which it arises. In searching for a theory of turbulence, perhaps we are looking for a chimera. Chimera is a mythological figure. He almost went to the extent of saying that turbulence might not even exist because we cannot understand it. So turbulence may not exist. What we see is merely a myth. So obviously that was in jest, but him expressing the despair in turbulence again. Finally, the quotation by Bradshaw. Bradshaw has authored several books on fluid mechanics and turbulence. He said turbulence was probably invented by the devil on the seventh day of creation when the good Lord wasn't looking. So again, another comment made in jest. So this sort of summarizes the complication associated with understanding turbulence, isn't it? We are trying to understand a topic that is so difficult that mathematicians and physicists are coming up with different kinds of explanation. Maybe it doesn't exist. Maybe I'm not hopeful about ever understanding turbulence. So that leads us to the question, why study turbulence? Right? Why is everybody spending all this effort and energy on trying to understand turbulence? It must be there everywhere. And the answer is right. It is there everywhere. Almost all fluid flows that you see out there in engineering and in nature is turbulent. Laminar flow is the exception. So you have two kinds of flows, right? Laminar flow and turbulent flow. This class is about turbulent flows. What is laminar flow? Firstly, what is laminar flow? So if you have a flow that is smooth, that is very regular, you could classify that as laminar flow. It flows in layers. It is predictable. It does not have chaotic motions. On the other hand, turbulent flow is a chaotic state of motion. It has irregularities. It has recirculations. It has fluctuations in space and time. What you see at one moment, you might not see it at the next moment. You might not see it ever. A phenomena that you see in the flow, you might not see it ever. It might not repeat. That's a turbulent flow. It's chaotic. Now, why do we want to study turbulent flow? It is really one of the most intriguing and frustrating, important problems in classical physics. Other examples of problems in classical physics, chaos, astrophysics, and turbulence is one of the most important. It's sometimes called the last unsolved problem. It's one of the most important problems in classical physics. But it is also intriguing and frustrating. Frustrating because we are not able to understand it completely. So I've shown here a few pictures just to illustrate what different kinds of turbulent flows look like, and at different scales. The first one is a cigarette smoke. There are analogies of what is happening in the flow in a cigarette smoke to black hole physics. The second picture is the flow behind the hull of a submarine. So you will have both laminar and turbulent flow here. The third picture is the turbulence in the tip vortex of an airplane wing. And the fourth one is a forest fire. So sometimes when I try to describe the differences between a laminar flow and a turbulent flow, I say, take a candle and take a forest fire. Do you see the difference? Both are fires, but do you see the difference in which they behave? A candle has a laminar flow, and because of that, it has a smooth edge, a well-defined edge. It is not chaotic. You know exactly how it is going to flow. On the other hand, a forest fire is very unpredictable. It has irregular motions. It burns vigorously. That's a turbulent flow. So these examples that I showed here have a lot of implications on trying to understand different phenomena. I mentioned that the cigarette smoke, the patterns that you see here have analogies to black hole physics. So trying to understand things in space, you might be the understanding the cigarette smoke could have a lot of implications in that. Trying to understand the wake behind a submarine, the flow behind the submarine, could have implications on how you design the hull of a submarine. Of course, the tip vortex on an airplane wing could in fact determine how you design the wing. Forest fires, again, trying to understand how they are generated and propagated can help us understand climate dynamics, weather patterns, in order to see how they can be stopped, for example, and what implications they have to changing weather conditions. So in that sense, the turbulent flows have a lot of different applications, right? I showed 4 examples in aircrafts, in space, related to space, in water through a submarine, and something like forest fires. But they have a lot of other applications. You see them both in natural and industrial processes. You see them in the atmosphere and oceans. There is turbulence in the oceans that could have implications on the wind patterns, the change in weather. Engineering applications, of course, simplest example is automobile aerodynamics or aircraft aerodynamics. Environmental flows, again, wind flows, atmospheric boundary layers, trying to understand that could have a lot of implications to understanding weather. And astrophysics, which have a lot of role to play in interstellar gas dynamics. So clearly, they have a lot of different applications in and around us. And what characterizes the turbulent flow from, what differentiates, I should say, the turbulent flow from a laminar flow is this irregular fluctuations, eddies as we call it, recirculation motions. And something else that we'll describe in a lot more detail in the coming classes is the enhanced mixing. The transport, the enhanced transport of mass, momentum, and energy. Now, this has a lot of implications in an engine, in an aircraft engine, where you are burning fuel and you want the fuel to mix with the oxidizer very fast. So you would want the flow to be turbulent so that it helps you mix the reactants and the oxidizer on a much faster time scale compared to if the flow was laminar. So it is essential to have a turbulent flow in an application like that. And a wide range of interacting scales. Now this is one of the biggest characteristics of turbulence. The fact that you have a wide range of length scales, from large scales to small scales. And we'll illustrate some pictures showing that as well. So I list here some examples of where turbulent flow occurs, and I'm trying to show a wide range of applications, starting from the interior of biological cells. So here the turbulence that you observe is different from what you see in inertial systems. Like, what I mean is an engine or a pipe flow, a turbulent flow in a pipe, or a turbulent combustion phenomena in an aircraft engine. It's different. However, there are swirling chaotic patterns due to the active forces within the cell, and that can lead to some turbulence in the interior of biological cells. So it's in a very small scale, correct? Circulatory and respiratory systems of living creatures. Several technological devices, aircraft engine I mentioned, household appliances, for example, a washing machine. The swirling of the flow, water and clothes inside a washing machine has a turbulent flow in there, and that helps in mixing and getting the dirt out because you have an enhanced mixing because of the turbulent flow. Geophysical and astrophysical phenomena, including planetary interiors, we mentioned that. So that you see turbulent flow there. Oceans and atmospheres. So ocean flows, for example, you will have currents which are turbulent, mixing of water layers, which are again follow turbulent flow behavior. swirling eddies due to the winds, temperature differences. So trying to understand that has a lot of implications on trying to understand how the heat is transported and essentially how seasons change, how climate changes, and galactic and supergalactic scales. So a wide range of applications as we see here. And these are some of the reasons why we have to study turbulence. So despite despite turbulent flow occurring in a wide range of applications, both in nature and engineering, okay, we call it the ubiquity of turbulence, meaning it exists everywhere. The problem of turbulence, we call it problem of turbulence because it really is a problem. It's one of the last unsolved problems in classical physics, right? So it still remains an unsolved problem even to this day. And understanding turbulence is a challenge. It's a significant challenge. So I'd like to show you this picture which illustrates one of the complications in understanding turbulence. Its range of length scales. Here I have a turbulent jet. Jet is issuing from some kind of nozzle, say for example. This nozzle has a diameter d. Okay. Now the jet is issuing from the nozzle, and what happens is because of the fact that the flow is turbulent, it starts to break up. You see some vortices being developed here. These vortices eventually break up into smaller and smaller vortices. And what you see is a nice jet that has evolved as it's going from left to right. This is what has happened. If the flow was laminar, you wouldn't see structures that look even close to this. You would see the same jet, you would see something like this. So let's say I have the domain, I'm going to draw it here. Let's say you have the nozzle, you would see something like this. Almost like a candle flame. Very smooth edges, well-defined edges. Compare that to what you see here. Okay, so this is laminar. And this is obviously, just a second, this is obviously turbulent. But what is one of the main things that you notice in this figure? It's a turbulent jet, and you notice these patterns that one is very different from the other. They are similar, some of them are similar, but it's just very different from the other. You have these patterns, some are small, some are large. And you have also patterns that are in between. So you have a large structure shown here, okay? Then you have a few small structures, and you have some structures that are in between, that are between the large structure and the small structure in size. So typically the largest structure will be of the order of the diameter of the jet, d. And the smallest structure could be as small as a few thousandths of the largest scale. So we are talking about, for example, if the d is, say, 1 centimeter. If the diameter of the jet is 1 centimeter, then you have length scales, I'm going to call that L, ranging from 1 centimeter all the way down to 0.001 centimeter. I'm giving you an example. It could vary. It could be 0.01, it could be 0.0001, and so on. That depends on certain other conditions, which we'll cover. But we are talking about ranges of length scales that go 2 orders of magnitude, 3 orders of magnitude, 4 orders of magnitude, depending on what the Reynolds number of the jet is. and I'll describe Reynolds number in more detail in the next few classes. But the range of length scales that you have, the wide range of length scales is staggering. On the other hand, if you have a laminar jet, and let's say you have a 1 centimeter nozzle, D is again 1 centimeter. The largest length scale and the smallest length scale are of the order of 1 centimeter. All length scales are of the order of 1 centimeter. It could be 0.8, 0.9, 1.1, 1.2 are of the same order. Whereas in a turbulent flow, we are talking about length scales that span several orders of magnitude. So I just gave you an example where it spans 3 orders of magnitude. It could be 4, 5, and so on. So that is the difference between a laminar flow and a turbulent flow. And this is the most important point, the wide range of length scales. There are other attributes that make a turbulent flow a turbulent flow, but this is one of the main attributes, the wide range of length scales. For a first class, this is what I wanted to illustrate. So this has been studied by some of the greatest physicists and engineers in the 19th centuries, right? And we still don't understand in complete detail, okay? We have made a lot of strides in understanding turbulence. And you will see in this module, when I talk about the history of turbulence, how physicists have spent a lot of effort into trying and understanding turbulence through different approaches. We have made a lot of strides. But we have still not understood in complete detail why and how turbulence occurs. Okay? And can we predict turbulence with any degree of reliability? That's the key here. Because everywhere you will see that whichever approach we use to understand turbulence, we are making some assumption. It is not complete by any means, even in some simple flow situations. So I'm presenting here the motivation. I'm presenting the reason for why we need to study turbulence. So one of the reasons is the practical utility. Right? It has a wide range of applications. We talk about it being present in the human body, to engineering applications, to intergalactic scales. So nature, engineering, and a wide range of applications. A lot of technological devices use turbulence. Designing that means understanding turbulence to some level of detail so that you can design that in a proper way, so that you can improve the efficiency. So that's the practical utility. But also, there is an intellectual challenge to understanding turbulence. The intellectual challenge has to do with the fact that there are so many complications associated with this phenomena. The wide range of length scales, the unpredictability, the irregular patterns that do not repeat itself, the non-repeatability. That brings the intellectual challenge into play. So that is our motivation here. That is how we are addressing this question. That is how we are trying to answer this question. Why study turbulence? It is motivated by the inherent intellectual challenge and the practical utility. That is why we have to study turbulence. So what have we looked at in this class? We looked at the despair that different physicists have expressed. The despair in studying turbulence, because it is such a complicated phenomena. It is such a complex phenomena that a lot of physicists have only understood it to a certain extent. So a lot of them are expressing despair. Then we try to address the question, why study turbulence? Because of its intellectual challenge and practical utility. I showed you a picture of a turbulent jet illustrating one main feature, one main attribute of turbulence, the wide range of length scales. And a simple laboratory jet shows you how the range of length scales change from large scales to small scales. In the next class, what we will do is we will look at how can we define turbulence? Can we understand what it is? Can we describe what it is? So we will start with some descriptions of turbulence. Thank you.